This lesson is for section 14.2. We're going to be working on the second day of binomial theorem. Our objective for today is to evaluate or simplify expressions containing factorials or binomial coefficients. So I believe factorials will be review for you, binomial coefficients will be new, and then our second objective is, instead of using Pascal's triangle, we are going to now use the binomial theorem to complete binomial expansions that we were previously using Pascal's triangle to do. So let's start by reviewing the factorial symbol notation. So n factorial here, which is just n followed by an exclamation point, is simply the product of the numbers 1 through n, where n is a natural number. We also have this fact here, 0 factorial is actually equal to 1. If you want to see a proof on that, you can Google that, because I'm not going to prove that here. But basically, here's an example. 7 factorial over 5 factorial is just equal to 7 times every descending integer, so we get to 1. And then divided by 5 times the descending integers, and again until we get to 1. Now here we see that these can cancel, leaving me with just 7 times 6, which is really 42. So 7 factorial over 5 factorial can also be written as 7 times 6 times 5 factorial over 5 factorial, and these would cancel. So that's going to come into handy here when we look at n plus 2 factorial over n minus 1 factorial for some natural number n. So n plus 2 factorial is the same as n plus 2 times the next integer, descending integer, n plus 1, times the next descending integer, n, times n minus 1. And I'm going to leave that as n minus 1 factorial because I see in the denominator that I also have an n minus 1 factorial. So these would clearly cancel, leaving me with just n plus 2 times n plus 1 times n. So if I were to find this product here, I have n squared plus 3n plus 2 multiplied by another n, right? I just found the product here of these two binomials. And I'm left with n cubed plus 3n squared plus 2n. So that would be how I would simplify this factorial. I'd like you guys to try number 2 on your own, and then you can check with the key. And then we're going to get into the definition of the binomial coefficient in just a second. Okay, so to give you some background on the binomial theorem, we need to first discuss the difference between a combination and a permutation. So in English, the term combination is used pretty loosely. So here I've got two examples that are going to hopefully differentiate between the meaning of a combination versus a permutation. So if I were to say my fruit salad is a combination of apples, grapes, and bananas, it would be the same as saying, oh, my salad has grapes, apples, and bananas. Or ordering, for example, a pizza and asking, for the toppings and saying, I want green peppers, onions, and mushrooms. Even if you order that in a different order, onions, green peppers, then mushrooms, well, it's still the same pizza, okay? Now, the word combination is also used in reference to like lockers. People say, oh, my locker combination is 33-2-1. But here, the order is actually very important. If you were to try, 2-33-1 or 1-33-2, even though it's the same numbers, it won't work, right? Our locker would not open. It has to be exactly 33-2-1 in that specific order for that to work. So if the order doesn't matter, we call that a combination. If the order does matter, it's considered a permutation. So in binomial theorem, we actually use combinations. I'm just going to reiterate the idea of a combination here by using these three boxes, okay? A red, a blue, and a green box. Now, if I were to ask you to do a combination of these, there's only one grouping, right? Red, blue, or green, even if I had it shown as blue, green, red, is still the same. You still have the same combination of these three boxes, okay? In other words, my salad has the same 3 toppings no matter what. So order does not matter. If I ask you to do permutation, however, those 3 boxes can be ordered differently, okay? So in other words, my locker combo, which I'm putting in quotes because it's not really a combination, is 33-2-1. There's a specific order to that. Order matters here. Now, in that case, you could see 6 different possible permutations for the same group of objects, whereas you're only going to see one combination, okay? So in other words, you really shouldn't call this a combination lock. It's really a permutation lock. So if I were to consider red, blue, green a different grouping than red, green, blue, I'd end up with 6 different permutations for those same 3 blocks as opposed to just one combination. Now here I've increased the number of boxes, the different types of boxes that you're going to see here. So we now have a purple and a yellow box. So of these 5 boxes total, how would I be able to group 3 of them and make different combinations? Okay, so basically, if I were to take a red, a blue, and a green and group those together, so this is one grouping, okay, that is not different, even if I'm going in a different order and taking blue, then red, then green, we're considering this the same exact combination, okay? So that's what a combination is. These are not distinct from this grouping here. So we wouldn't want to use that grouping. However, we could use this as another combination here, okay? So in a combination, we have to have 3 distinct, right, groupings. Well, how many would I be able to make? And this is where the binomial coefficient comes into place. Instead of having to sit here and try to, you know, figure out all the different possibilities, we're going to use the binomial coefficient. So here's our definition of the binomial coefficient. Now, what this formula here allows us to do is exactly what we were just trying to figure out with those square, you know, those boxes that we were just looking at. We had 5 squares, and we were trying to group that into 3. So we were trying to take 3 distinct boxes and figure out how many different groupings we had. Well, this formula will allow us to do that. When you see 5, choose 3, that's how you actually read that. So this is read as n choose k. And for example here, it would be 5 choose 3. You can use this formula to figure out the total number of combinations. So here, 5 choose 2, we would write that as 5 factorial over 2 factorial times 5 minus 2 factorial. And this ends up being 5 factorial over 2 factorial times 3 factorial. And if I simplify here, 5 times 4 times, I'm going to stop at 3 factorial because I know that I have that 3 factorial here that will cancel. And I end up with 5 times 4, 20, over 2 times 1, 2, to give me a total of 10 combinations. So if I went back to that slide here, I would be able to make 10 different combinations of different groupings of 3. Now what I find interesting is that 5 choose 3, if we calculate here, 5 choose 3, which would be 5 factorial over 3 factorial times 5 minus 2 factorial. Well, this, oh, sorry, 5 minus 3 it should be here. This ends up being 5 times 4 times, again, 3 factorial over 3 factorial times 2 factorial. Notice that these 3 factorials will cancel, and I'm left with 5 times 4 over 2 times 1, which is, again, 10. So 5 choose 2 is the same as 5 choose 3. So to just get you thinking about why that is the case, I'm going to ask a question to you. Let's say you're the captain on a sinking ship, and your lifeboat can only hold 5 people. You've got 15 total people aboard and only room for 5 people on each lifeboat, or on the only lifeboat that you have. So how would you decide who gets picked? Well, you could tell your, the people on the board, well, guys, I have 15 of you and I can only choose 5, right? But a nicer way of saying that, same idea, would also be to say, I've got 15 people here, 10 of you get to stay, okay? It's the same idea as taking 5 away from the group as leaving 10. And that's why 15 choose 5 is the same as 15 choose 10. Okay, and we just saw 5 choose 2, when we calculated that, was the same as 5 choose 3. Alright? Now, binomial coefficients are named that way because they are actually the coefficients when we expand a plus b to the n. So the coefficients of a plus b to the n are the n plus 1 numbers, n choose 0, n choose 1, n choose 2, all the way till we get to n choose n. Now, it's easy to see that here in my example. So let's consider the expansion of a plus b to the 3rd power. Okay. Now we know from Pascal's triangle that those coefficients would be 1, 3, 3, 1. Right? We can write out Pascal's triangle and find these. So notice that here, when we take 3 choose 0, we get 1. When we take 3 choose 1, we end up with 3. And, of course, 3 choose 2, these should be equivalent. They certainly are. We get 3 again. And 3 choose 3, which should be equivalent to our first one here, 3 choose 0. We also end up with 1. These end up being the coefficients for that binomial expansion. So it's why it's called the binomial coefficient. Okay, so it was clear that the binomial coefficient becomes the coefficient for your binomial expansion. But I want to explain why they're combinations as opposed to permutations. So let's talk about a pretty concrete example, a plus b to the fifth. So let's write this as the product of all the factors a plus b. And you could obviously find you know, the terms here by multiplying this out by brute force, but of course that would be crazy because you can use your binomial expansion using Pascal's so far, because we haven't yet talked about here the binomial theorem yet. We'll get to that in a second. Now, what I want to look at is, let's say I wanted to get a term a squared b cubed. Okay, a squared b cubed. Well, I have 5 different a's that I can choose from, right? And I want to pick 2 of them. That's like saying 5, choose 2. Now, for the whole term though, a squared b cubed, think about it this way. You've got, let's say I chose this a and this a, and then this b, and this b. Well, even though I might choose them in a different order, like say I chose this a, and then I skipped and I picked the b here instead, and then I chose this a, and then this b and this b. Well, that's a different order that I chose, but still results in the same exact expression of a squared b cubed, right? Well, I would have 5 choose 3 options here. This term will actually be the same as your exponent for b. Now, it's the same as 5 choose 2, right? We already know that those are equivalent, so if you're wondering, well, why can't I write that as 5 choose 2? You could, but it's actually more convenient when we start getting to very large values for you to write it as 5 choose 3 instead, to match the exponent for your b term as opposed to your a term, okay? So you may be wondering why we need to use binomial coefficients. Well, it actually becomes very helpful to use those binomial coefficients in the binomial theorem, because when you do really large expansions, it's really inefficient to try to use Pascal's triangle. It just doesn't make sense to have to write out all of those rows and do all that computation yourself. So we use the binomial theorem, which is written here, okay, and I'm going to use an example just following here this notation. This is n choose 0 times a to the nth degree, okay, and that makes sense because our first term should always be 1 times a to whatever that degree is, and b to the 0 power, okay. So I want you to notice, since this is b to the 0, these are actually the same. This is the exponent of your b term. And we're going to look at that a little bit more in depth tomorrow in the next video. But basically, let's say I had a plus b to the 4th. Well, that's going to equal 4 choose 0 times a to the 4th, and then of course times b to the 0, and plus 4 choose 1, a to the 3rd, b, plus 4 choose 2, a to the 2nd power, because I'm going to descend my a term by 1 degree, and then I'm going to increase the b term by 1, and so I'd have b cubed. I'm sorry, b squared. And then 4 choose 3, a to the 1st, b to the 3rd, and then finally 4 choose 4, a to the 0, b to the 4th, so of course just b to the 4th. Now, if I were to actually calculate and do this computation here for 4 choose 0, we know that that's 4 factorial over 0 factorial times 4 minus 0 factorial, just from using our formula from above. And here, clearly, the 4 factorial and the 4 factorial will cancel. 0 factorial is just 1, so we're left with a coefficient here of 1. And that does make sense, and it follows using Pascal's triangle. And if I were to calculate each one of these using the binomial coefficient definition, well, I'm going to get 1, 4, 6, 4, 1, which is the 5th row of Pascal's triangle if you count a to the 0. That first row is 1. All right, so kind of interesting. Pretty crazy that somebody came up with this in the first place. But basically, now that we know this, we can use this idea to do very large expansions, like here. We're going to expand this binomial, which is to the 31st power here. I'm not going to ask you to do all 32 terms. Remember, there would be 32 terms here because it's always n plus 1 number of terms. But we're only going to do the first 4 because that would be insane of me to ask you to do all 32. But instead of using Pascal's, which was what we did yesterday, That would be crazy again to try to draw out that triangle and go all the way down to the 32nd row. We don't want to do that. We're going to use binomial theorem instead. So let's start by just using, let's use a and b for right now. And then we're going to replace a and b with x and -2. So we have 31, choose 0. Then a to the 31st, and b is, remember, is the same as that exponent here. So I'm going to get rid of that b to 0. Then plus 31, choose 1, a to the 30th, descending exponents for your a, and then b to the 1st power, plus 31, choose 2, a to the 29th, b to the 2nd power, and then my 4th term that we're going to find, we're going to stop here after 4, but 31, choose 3, then a to the 28th, b to the 3rd. So if we were to substitute in here, we have 31, choose 0, x to the 31st, then 31, choose 1, a to the 30th times -2, then 31, choose 2, a to the 29th, and -2 squared. Then 31, choose 3 times a to the 28th. Oh shoot, I keep saying a and that's supposed to be an x. Sorry. There's an x here, x there. So x to the 28th and -2 to the 3rd. Okay, so now let's look at each of these. I don't want you to have to do these by hand, and in fact we can actually use our calculator to do these from now on. So since we know the definition, I'm not going to ask you every single time to do these computations, although you should be able to do it by hand as well. You will be assessed on your ability to do that by hand. Okay, so here we go. 31, choose 0. Well, I know that's going to be 1, right? We know that the first coefficient here should be 1, but let's show it in your calculator how to find that. What you're going to do is hit math and go all the way over to probability, which is all the way to the right, PRB, and we're going to go down to n choose R. Okay, n choose R, NCR. This is the button that you're going to hit. Now, we need to have an actual number in there before, so I should have cleared that out. Let's type in 31 first, and then we're going to hit math, scroll over to PRB, probability, go down to 3, hit enter, and then choose 0. We should end up with 1, and in fact we do. So this is how you're going to be able to calculate that. Now, instead of having to do this every single time, make sure you just do the shortcut here, second entry, so that it brings up that last entry here. So then when we do 31, choose 1, we end up with 31. Second entry, 31, choose 2, will give us 465. So imagine if we were to try to do Pascal's triangle and be adding all of that together. That'd be kind of crazy. So especially if you were off by even just like a single integer, you'd get crazy numbers and crazy answers. So anyhow, here we go. So this is now 1 x to the 31st plus 31 x to the 30th times -2. So I'm going to simplify that to -62 x to the 30th. And we just found that this was 465 x to the 29th times a positive 4 here, right? It's -2, that base, squared. So now we're going to take 465 times 4, x to the 29th, and then let's do 31, choose 3. So, whoops, just hit second entry, bring it last up, hit 3 here, and we have 4,495. Again, so big, and we're just into the 4th term. So 4,495 x to the 28th times that -8. I'm going to stop here for that simplifying, but basically from here it's pretty easy. It's very similar then to Pascal's with how we finish that problem off. Okay, now I just wanted to point out one more problem where we have an a and b term that look a little bit more complex, but it's still the same idea. Let's expand the first 4 terms only, so let's only do the first 4 terms for an expansion to the 46th power. Okay, so we've got 46 choose 0 times the square root of x to the 46th power plus 46 choose 1 times root x to the 45th power multiplied by I over x to the first, then plus 46 choose 2 times the square root of x to the 44th power times I over x squared, and then let's sneak this last one in down here. I'll just move this over. So then plus 46 choose 3 times root x to the 43rd power multiplied by I over x cubed. Okay, so I hope that sticking that in your calculator is now pretty straightforward for you, so I'm not going to compute all of these coefficients. I just want to talk about how you would simplify here. So this is x to the 1/2 to the 46, so that would become x to the 23rd. Here we'd have x to the 45 halves multiplied by I over x. Now, since we have the same base here, we can simply subtract exponents. So 45 halves, and this is to the first power, so we're going to take 45 halves minus 1, so 2 halves is 43 halves. So we have here x to the 43 halves multiplied by I. Okay. Then over here in this term, root x to the 44th power is just going to become x to the 22nd power. Here, I squared over x squared. And of course, you want to simplify I squared. We talked about that last chapter. So we have x to the 20th times -1. So that's going to change that coefficient here to a negative. And then from here, I think that it's pretty straightforward, what your expectation is for what you're supposed to do. If you want to finish off both of those problems, and then I also have a third problem here for you to try on your own, you may certainly do so. But the idea here is that you're now using the binomial coefficient, n choose r, in order to do those calculations. All right, that's the end of the lesson. Nice job. I'll see you in class tomorrow.